Welcome back. Let's talk about containers. First, let's look at some general concepts, and then we'll get into code in considerable detail. So examples of containers include things like stacks, queues, trees, hash tables, things like that. These are also known as abstract data types. Now, to understand this stuff, it's good to kind of chop it up. And the first way that we can chop this material up is separate data from operations. So in a container, like a stack or a queue or something like that, you have data organized in some particular way. And then you write code that manipulates that data. So we call that data and operations. So what are some of the ways that you can organize data? Well, you could just have simple variables like X, Y, Z floating out in your code, floating around. And if you did that, then there's only certain kinds of ways that you could manipulate that data. Now, the next most complicated way that you could organize data is put it in an array. Now, if you put data in an array, then what would you do to it? What are the operations that you would write on that? Well, you might want to search it, that is, look for an item in the array, or you might want to bubble sort it, or select sort it, or do some kind of sorting operation. So if you organize data in an array, then that leads to something like a bubble sort or a selection sort or an insert sort or a merge sorter, some kind of sorting algorithm. So the way that you organize data affects the kinds of algorithms that you're going to write on that. Now, there's other ways to organize data. One way that we're going to look at in a little bit is linked structures. So for that, you have little chunks of data, and then you have pointers that point to other chunks of data. And using that, you can construct pretty elaborate structures like trees and graphs. And once you have a tree or a graph, then there's other things that you might want to do to it. There's certain kinds of algorithms that you might want to write. Like you might want to search a tree or insert an item into the tree. Or in the case of something more elaborate like a graph, you might want to, say, find the shortest path through a graph or find the total cost of a path or something like that. So the way that you organize data affects the kinds of things that you can do to that data. And those things that you're doing to the data, the operations, are going to have various time complexities depending on how the data is organized and what you're trying to do. All right. So that relationship between data organization and algorithm and how one affects the other, that's a fundamental idea in the study of data structures. Okay. So this separation between data and operations, that's one way to think about containers. Another way to think about containers is separating interface from implementation. So what is an interface? An interface is the set of functions that you use to access the data in a container. So for example, you might want to write a program that, let's say, counts sheep. So let's call that program that counts sheep, let's call that a higher level algorithm. And you might want to put your sheep somewhere. So you could put your sheep in a little container, and that might look like this. So you have an algorithm to count sheep, and it puts those sheep in this container by calling these foo functions, foo1 and foo2. Now, these foo1 and foo2 functions could be implemented in different ways depending on how the data is organized. That is, there could be an array in here, or there could be a tree in here. Who knows? But the algorithm up here doesn't care. It just calls the interface foo1 and foo2. So over here in this other little diagram, I have the same algorithm, but it's using a different container, container 2. So container 1 and container 2 have the same interface because they have the same functions, foo1, foo2, foo1, foo2. So the sheep counting algorithm up in here can use either one of these things, and it doesn't care. So that's the idea of interface versus implementation. That once again, these two containers here, in this case, they provide the same interface, that is, the same functions that are used by a higher level algorithm. But inside these functions here, which you can't see, of course, is presumably a different data organization and a different way to access that data. That is a different implementation. Here's another way to think about this thing is cars in the real world. So most cars that have the same interface. They have a steering wheel and some pedals on the floor, and you can get in any car and drive it pretty much the same. But what happens beyond the interface, that is the implementation of the interface, is considerably different. Consider a Ferrari and like a Toyota minivan. Now, they both have gas pedals. So you get in them and you step on the gas and it goes. But when you step on the gas in a Ferrari, the engine is quite a bit different than the engine inside a Toyota minivan. So you still drive them the same. They have the same interface. But inside, underneath, the machinery that implements that interface is different in these two devices. So why would you choose one versus the other? Like, why would you choose a Ferrari versus a Toyota? Well, it depends on other factors that come into play. Like, let's say you were really in a hurry to get to work, then you might choose a Ferrari. That'll get you there real quick. But on the other hand, let's say you had a whole bunch of people that you wanted to take, then you might take the Toyota. But they have the same interface. The way that you get there is going to be the same. You're still going to be stepping on pedals and turning wheels and stuff. All right. So let's look at a programming example to try and get this a little bit more concrete. So here I have a simple container. I'm calling it a list. And what I'm trying to do here is make just a real simple container without a lot of features. So this guy only does two things. It has an append operation and a remove operation. So I can put things in the list and I can remove things from the list. So I could use this to count sheep, for example. So I could have several different implementations of this interface, right? The append and remove functions make up the interface to this list container. So one implementation that we're going to look at is something called a circular array implementation. So in here, you're just taking an array and you're treating it as if it were a circle. So the array has indexes from 0 to size -1. And we insert, or that is we append operations at the tail, and then we remove items from the head. So let's say we did append A, then append B, and then append C. The data would look like this. First when this guy starts up, the head and the tail are at 0. And then you append A, and the tail moves down once. And then you append B, and the tail moves down once. So I guess really, the tail would be ready for the next item here. And that's kind of an implementation detail, but broadly speaking, the tail points to where you're doing the appends, and the head points to where you're doing the removes. So why would you use an item like this? Well, this is good for something like a serial communications buffer. So in a computer, there's a lot of data that's moved around serially, that is 1 byte at a time. You typically have 2 processes accessing this shared memory location. So you might have the CPU, for example, reading data from the head, that is removing data from the head. And then you'd have the network card appending data to the tail. So those two guys are kind of taking turns accessing this, and the serial data card might append a little bit of data, and then the CPU would read a little bit of data, and then back and forth. You'd append a little and read a little, and append a little and read a little. So this little chunk of data sort of moves around the buffer, kind of logically. It's never moved as a chunk, but you write to one end and you remove from the other end. So the net effect is over time is you'd see this little section of data kind of like moving around. So that's very efficient because you're never moving a big block of data. You're just writing to one end and then removing from the other. and no big chunks of data have to be moved all at once to another location. So for something like serial data communication, this is a very efficient operation. In code, this would look something like this right here. This right here, these few lines of code define how the data is organized. It's just a simple array, my list, of a size, in this case 10. And then I've got a couple of variables, head and tail and used. So this is the data organization. And then when we get to the size -1, we have to wrap around to 0. So we're going to be adding at the tail, and the tail will keep moving around like this. And then we'll be removing at the head, and the head will move around like that. When the tail gets to size -1, it has to go back to 0. So to do that little trick, we're doing this modulo arithmetic here. We're moving the tail down by 1 and then modding by the size. And this will, when it gets to size -1, it'll roll over back to 0. So this is the logical, what we say, logical treatment. That is, we're taking an actual simple array and we're treating it as if it were a circle just by doing this modulo arithmetic. That's what we mean by the term logical circle. Okay, so this is one particular data organization. And here's the append function, and we'll go through that in a little more detail. And then there's a remove function. Okay, so here's the append function. We'll look at that, and then here's the remove function. And append takes a character element D and sticks it in here, and then remove goes to the head and finds an element and then removes it and returns it as a character. So it's character remove void, and void append character D is the details of the interface, right? The interface consists of the remove function and the append function, and the data organization is this circular array. Okay, that's one implementation of this list container. Let's look at another implementation that we could do. We could use a linked implementation. So here we have little chunks of data called nodes, and they contain the data in them. And then they have these arrows, which are pointers that point to the next data element. So this is the same ABC thing, but stored in a different data organization. So here's the code details that defines this data organization. You've got something called a node, which is known as a self-referential data structure because it has a pointer of type node that can be used to point to another node. So in here we have the data element, in this case A, and then we have a pointer to the next element. So the data would be stored in this variable D, and then the pointer or the arrow in the diagram here would be stuck in this element next. So this guy, yeah, and then you've got these head and tail pointers here. So this guy still implements append. Here's append for this linked implementation of the same list container. So void append character D, and then I've got a remove function over here that character remove void. Okay, so the linked implementation has the same interface. It has a remove function and an append function. But what's going on inside here in the details of this particular linked implementation is different. Okay, so a high-level program that was counting sheep would just be calling append and remove as necessary, and it wouldn't care about what's happening in here. It could use this linked implementation, or it could use the previous circular array implementation over here. All right, that's the basic idea of a container. So I guess just to summarize, I could draw a little picture here. So we have a count sheep algorithm, and then it's calling basically it's calling basically append and remove. And inside here you could have the data stored in this circular array. So you could do that. This is count sheep. Or I could take the same count sheep algorithm, and it could call another implementation that still provides the same interface, append and remove. But the data inside here is stored with a different organization. Right, so the count sheep algorithm doesn't care which one of these guys it uses. This is like the Ferrari, let's say, and this is like the Toyota minivan. And you might choose one or the other depending on some details of these implementations. Now, these are such simple containers, append and remove, that the differences between these two operations are not really that important. But generally speaking, and we will see this in a little while, generally speaking, one of these implementations may be more appropriate than the other implementation for certain kinds of algorithms up at the top, right? For example, to use that Toyota and Ferrari algorithm, you may want to, this one. There's certain reasons you'd use a minivan versus a Ferrari, just like there's certain reasons you might use a linked implementation versus a circular implementation. And to understand that better, we have to look at some actual code, and so let's do that next, okay? So what I'm going to do now is go through these documents that are posted that provide a complete implementation of a list with a circular array data organization. So let's just go through this in super duper detail, all right? Line by line. Okay, I've got my data organization here. It's just a simple array with 10 elements in it. I've got some indexes to point at the head and the tail and used, and these are both initially equal to 0. And let's see, and then this is the interface. So I've added a couple of more functions. So we've got remove and append, but we've also got find, traverse, is empty. So these 5 functions together define the interface to this list container. The data is being stored in a circular array, which is just an array that we're treating logically as if it were a circle by doing modular arithmetic past the size minus 1, which in this case is 9. All right, so a testing script, that is what I'm calling main here. I'm calling it a testing script because it exists solely just to exercise the interface. That is, we're going to call all these interface functions: remove, find, traverse, and is empty. We're going to call all of those guys. So we got to do an initialization somewhere. So I did it here in main, although you could do it up in here depending on the language. I think C++ lets you do it up in here. But anyway, this just initializes the array. And then we're going to call append A, B, C, D, E, F. And at that point, the thing looks like this. That is, A gets stuck here and the tail moves down, and then B gets put in here and the tail moves down, etc. And then when we're all done, we have A through F, and then the tail has a value 5, and the head has a value 0. And used would be 1, 2, 3, 4, 5, 6. Okay, then we can call find, and find, what does find do? Find removes a data element, so we're going to do a find on X, but there is no X, so it won't find it. Then we'll do a find on D, and it'll find the D and remove it. Then we'll just do a remove, which will remove from the head, and we'll do another remove and remove from the head. In between there, we're doing a traverse, so we do. You can see on the output what's happening over here. So first, I fill the list, and then I do a find on X, and it says it's not found, and then I do a find on D, and it says it's found, and then I do another traverse, and it goes through the items, and you see D has been removed by the found command. Then I do 2 removes, and I get A and B, and then I do another traverse, and then empty the list with using this little loop right in here, where I just call remove until it's empty. All right, so this is just a testing script that you use to exercise the interface. That is, call all the functions in the interface to show that they work. And you would get some output like this that would, that should correspond to what you're doing in main here, all right? Okay, next we can just sort of look at each one of these functions and go through them in detail. How would they be implemented? All right, so that's what I'm going to do now. So the first guy is append. So what I've got here is a kind of a diagramming method to document what is happening in the code here, to document and help explain what's happening. So here's what append does. So first we check if the list is empty, and we can use the used variable to check if the list is empty. And if it's empty, then all you need to do is put the data at the tail. So that's this line right here. And then increment used to 1, and then leave, and you're done. And then I've got a little check in here to prevent overflow. That is, if the circular array is completely full, and that would be indicated by the tail being just before the head here. And if that's the case, then it'll just return. It'll print a message and return. And then otherwise, we insert the data at the tail. So that's what this little diagram here is trying to show. So if the list is not empty, then you put the data element, first you scoot the tail down, tail equals tail plus 1, and then you insert the data element at the tail, and then increment used. So used is necessary because of an implementation detail, because initially you have to decide how you're going to handle the head and the tail, and I decided that they would initially point to the first item, or they'd point to 0. So there's no way to know if this guy has any elements in it, so I'm using used for that. So just a little detail there. Okay, and then this modulo size, this is so that when we get to element 9, we roll back to 0 by modding by, in this case, 10. Okay, so that's append. Let's look at the traverse algorithm. So traverse just walks through this guy and prints out items that are in here. So let's walk through it. So we got a character or we've got a pointer. Now I'm calling it a pointer, but strictly speaking, it's really an integer. I mean, a character is sometimes referred to as a little integer because it can contain the value between 0 and 255. So we need this p because we're going to walk this p pointer down through the filled part of the array. So there's a couple of situations we got to check for. It might be empty, in which case you just print that it's empty and then return. And there might be one element, in which case the logic is pretty simple. You just print the data that's at the head of the list and then leave. And then it might be more than one element, in which case you need to point to the head and then walk the head, or walk P down to the end, in this case one element past the tail, printing along the way. So I wrote a do loop here, and I'm printing first P points to the head, and then I come into the do loop and I print the element at the pointer at the head, which is the same as P, and then start walking P down by incrementing by 1. And then once again we got to account for rollover when we get to 9, and we keep walking until the pointer P is 1 past the tail here. That's what this logic says pretty much. Okay, so this is traverse and the code, and then a little diagram. Okay, moving right along, we've got remove. So remove removes from the head. So we're looking, we're going to the head and just returning a copy of that in temp, and then we're scooting the head down. Okay, there's a couple of special cases where it could be empty and it could be one element. So if it's empty, there's nothing to remove, and you just return -1, which would be interpreted as false from the calling side of remove. Okay, then there's a special case of this guy, this list having just one element. You could check that by checking if used is 1. If that's the case, you're going to remove something, so you make use 0, and then you return the element at the head. And if there's more than one item, then you do this copy from the data that's in the head and put it in temp, and then scoot the head down by 1, and then decrement the used counter and return temp. So that there, you know, 3 special cases. Like the only time you have to move the head is if you have more than one element. So that's why I broke it up this way. So this is remove. Okay, we've got one last guy in here. We've got this thing. This is the most complicated one, where efficiency might start to come into play here. Okay, hope I remember to talk about that. So here's find. So what does find do? It searches an array, or in this case it searches the container here, which happens to be an array, for a particular item, and if it finds it, it removes that item and returns 1. If it doesn't find the item, it returns 0. So I kind of broke this up into 3 different cases. The first case is this guy could be empty, in which case it's just going to return false, just return 0, because there's nothing to do. Then there's a special case of this guy containing just one node. So you check if it's one node, and if it is, then you see if the data you're looking for is actually at the head, because you could be looking for some value that's not in here. So you check, is the single data element that's in this guy, is it at the only location available, which is the head, and it either is or it isn't. And if it is, then you decrement the used counter. That's sort of removing this guy. And then there's these guys you don't need to move, the head and the tail, because they both point to the same element when there's either 0 items in here or 1 item in here. Okay, so you just set the used counter to 0 and then return 1, indicating that you found the element. So if the element you're seeking is not at the head, then you just say not found and return 0. So that's that. That's the special case for is empty and for 1. Now the little more general case for if you have more than one item is considerably more complicated. All right. So what do we got to do here? We've got the head index, or head pointer, if you will. It's really an index that contains the array index for the start of this list, but sometimes you use the word pointer, even though strictly speaking it's an index. And then we've got the tail, which is here initially. And what we're going to do is we're going to take another index, P, which we initially set to point to the head, and then we walk it all the way down to the end of this thing, looking for the item that we are seeking. And if we find that item, let's say we find it here. Let's say we find the item we're seeking here. Then what we need to do is move everybody past that. We have to move everybody past that. We have to move them up 1. Okay? So that's what's happening in here. First I set P equal to the head, and then I go into this loop where I'm looking for this element D. D is what's passed in here. That's the element I'm seeking. And if I find it, I go into this scooting operation where I scoot all of these guys down. And then when that's all done, I have to move the tail back, right? Because there's one less item in the list. So you have to do this tail minus thingy. And then because you're moving the tail back, it could roll over past 0. So you need to check for that and correct for that. And then, you know, we removed an item, so we have to decrement used. Say that we found it and then return 1. All right, and the scooting operation, the scoot stuff after P up, is another loop that continues until P falls, until P gets to the tail. While P not equal to tail, it continues until P is pointing to the tail. And I think this guy's going, on my diagram, it looks like it's going 1 too far. P would be here, yeah. And no, it wouldn't, because it would get incremented 1 more time, and then that would make this conditional false. Actually, I'm not sure. It's some. I don't really want to spend the brain power on that right now, but it's something like that. Anyway, you guys can figure out those details, I'm sure. I just don't want to get too down into the weeds because I lose track of what it is I'm trying to do. But anyway, let's look at the structure of this thing and try and analyze the time complexity of this operation. All right. So I've got an outer loop do while P is not equal to the tail plus 1. So basically P is running all the way to the end here. So let's call that N. P has to go through N items here because it's looking for the item. In worst case, it's going to go all the way to the end because it won't find anything. Worst case, the item you're seeking is not here. But let's say you do find it. Then you go into this inner loop that does the scooting. So I wrote this on purpose as a nested loop, although it doesn't have to be, right? I could have written it a loop that starts here, goes to find, or goes to the found location, and then another loop after that that does the rest of the journey where we're scooting everybody down. So I could have wrote loop, you know, that a loop that terminates and then followed by another loop that terminates. So those two loops together would go through N if I wrote it that way. But instead I wrote it as a nested loop, but it still functions the same way, right? Because the outer loop goes until it finds it, and then the inner loop goes the rest of the way, scooting items down, and then when it comes out of the inner loop, the condition for the outer loop is false now. So it terminates. So basically, no matter what happens, this thing has to travel the entire length. So that the time complexity is N. It's N. It's big O of N, because where N being the number of data elements, because this pointer P always has to travel the entire width of this thing. So earlier we talked about how to analyze code using these so-called rules of thumb, and generally speaking, when we have a nested loop, we suspect N squared, right? But in this case, that's not the case because of the details of the way these loops are written. Okay, so you got to be careful with these rules of thumb when you're analyzing algorithms. They'll point you in the right direction most of the time, but not always. Okay, so once again, let me just say this P, it goes till it finds it, the data element, and then it goes the rest of the way. So it always goes the whole length. So that's N. All right. So what have we done? We've looked at these interface functions for the circular implementation in considerable, code line by line. And then when we get to this find guy, we have this N complexity. What's the complexity of the other guys? Let's just back up for a minute here. What's the time complexity of remove? How long does this take related to N? N being the size of elements or the number of elements in the array. How long does this take? If N were really big, would it take longer than if N were really small? No, because it's going to the head and doing a couple of checks and then leaving. It doesn't matter if there were 1,000,000 items in this guy or 10 items. It's only looking at the head. So this guy, it's really got big O of 1 for remove, because it just comes in here and does a couple things and then leaves. And this dude, What about append? Same thing. It goes to the tail of the list, does a couple operations, and leaves. It doesn't matter how big n is. It doesn't affect the time complexity. So this is also big O of n. Or another way to think about it, there's no loops in here at all. There's just constant time operations in here. So this is big O of n. What about traverse? What's the time complexity of traverse? Well, this guy's got a loop. You know, these are all constant time operations up here, so we can ignore them. But this guy's got a loop. And this loop goes the entire way. It goes, P starts at the head, and it goes to all the way to the tail every time. So this is big O of n. Okay? So that was one implementation. That was a circular array implementation of a particular interface. And this is the interface: remove, append, find, traverse, and is empty. And then we looked at the time complexities of each of these. This was big O of 1, this was big O of 1, this was n, this was n, and this was, well, we didn't look at it, but it's going to be big O of 1 because all it does is goes into, it looks at used. Okay, let's look at another implementation of this same, of a container having this same interface. Here it is. So this is a linked implementation of the same list container. This is the interface. There are functions, a set of functions having the same, return values and argument types. So the same set of functions, but inside the data is stored differently. It's stored in these links. And here I have a little testing program that's the exact same testing program, and it produces output like here, verifying that these in fact work. Okay, let's go through each one of these: remove, append, find, traverse, and is empty in exquisite detail. All right, sound good? So here's append. So to do an append to this guy, first you need a new node. So no matter what, you got to make a new node. So just outright do that. And this is how you do this if you haven't seen this kind of thing before. And so here I'm using the C++ new operator, which is just a convenient way. It's much better than malloc. So anyway, you make a new node pointer, P, and then have that point to a new node. So this is what that looks like. If you drew a little picture, you'd have the pointer P, and then you have the node that you just created using new. And P points to that. So P contains an address that points to a location in memory where this node is stored. So P in this case really is a pointer. In the previous implementation, I was loosely referring to P as a pointer, when in fact in the previous implementation, the circular array, P was in fact a character, which is a little integer. But here it's a pointer. Okay, then you need to tie up the loose end here. That is, you need to make the next pointer point to 0. Even though you're going to change that later, it's just being tidy, really. And then here we're putting the data element D that's passed into this node. We're putting that into this node. So if you haven't used pointers with to structures, remember this is a little structure right here. Right? We have a structure with a structure called node with a node pointer inside, and then a character pointer D. So the elements inside this guy are next and D. And when you're referring to the elements of a structure, you use this arrow operator to get at these two fields in here, the D and the next. Okay, so we put the data in here, D in there. Or just put a D in there. Okay, so we've got a couple of cases. It could be empty, which you indicate by the head pointer being nothing, which is what it's initialized to. If that's the case, you make the head and the tail pointers point to this new, point to the same thing that P pointed to. You do a line that looks like this, which I've indicated with a little diagram in here. So before, the head and the tail point to nothing. That is when the list is empty. Afterwards, P, our local pointer P, it's a local pointer, and then our global pointers H and T all point to the same new node. And we're done. That's the case, what we do if the list is empty. Okay, Okay, if the list is not empty, we need to append to the tail. So this is what that might look like. Let's say you had 3 items in this thing. So you'd have node, node, node. You'd have the head pointer pointing to this, and you'd have the tail pointer pointing to that. What you need to do is take your new node that you just created and scoot the tail down so that it points to the new node, and fix the next pointer in this previous node so that it points to the new node, right? So you'll have a 4-element thing with the head here and the tail pointing there. Now, there's only 2 lines of code to do that. You have to make sure you do them in the correct order, because right now before you do these 2 operations, the tail pointer points to this last node, and that gives you access to this next field. So you have to update that first. Otherwise, you drop this thing, essentially. Because T is like your leash. You could think of this node here as like a dog on a leash. So to get to this dog here and update his next field, you need to use T. So you do T next, which is this box, equals P. So you're taking the value that is in P, which is an address that points to this node, and you're storing that value in here. So this pointer points to this node as well. So you do that first. Then you update the tail to contain P's address. So P, which points to the new node, you put that address in T, so T will point to the new node. Okay, so this is basic kind of dealing with, sometimes this is called linked lists idea, and maybe you've implemented this in your beginning programming class, maybe you haven't, but I'm expecting you to play with this and study pointers in this context, and get to where you understand what's happening here. You can print out pointer values if you want, and study the numbers that you get, and draw these little pictures and study this kind of thing. Okay, so this is just the basics of creating nodes and hooking them up. That's append. Hey, what's the time complexity, by the way, while we're still here? Does it depend on n? No, it doesn't, right? There's no loops. There's just some constant time operations. So this list could be a jillion long, and appending isn't going to take you any longer, right? All right, let's look at, so it's big O of 1. It's big O of 1, constant time operation. Let's look at traverse, which is going to be big O of n, because it's going to walk through every element, okay, while we're talking about big O's. So this guy's got big O of n. What's it going to look like in detail? Well, I got to have a pointer to point to each one of these nodes one by one. So I make a new pointer called P, initialize it to contain the same address that head contains. So head and P both point to the same node here. Then I loop until P is 0, which would happen when P falls off the n here. When P receives the value that's in this last node, which is 0, it'll essentially point to nothing. Okay, and you print out the data that's in what P is pointing to. This is a typecast character here, because I'm using the cout command, which is trying to help you by interpreting the data a certain way. And I want to see a letter here. I want to see the letter A. So you may or may not need this depending on your compiler stuff. But anyway, and then I just scoot P down by taking the value that's in here and writing it back to P, which basically makes P point to the next node. Okay, so I'm doing this P equals P next deal in a loop until P falls off the n. And we end up looking at all n items, so the time complexity is big O of n. That's that guy. Let's look at is empty. Yeah, that's trivial. Let's look at remove and then find. Okay, remove removes from the tail, and it returns -1 if the list is empty. So we've got a couple of cases here that I've written out for you. First, we need a node pointer. And then we need a temporary variable because we're going to destroy the node and we would lose the value that's in there. So we need to store it first before we destroy the node. Then there's 3 cases is the way that I wrote this thing. That could be empty list, could be only one node, could be more than one node. So it's possible to write this all in one section, and you can do that if you want, but I like to do simple operations and try and get out of there as quick as I can, sort of thinking. It's just a code style. You know, do what you need to do or what you want to do. But anyway, if the list is empty, there's nothing to do, so just return false, -1. Okay, if there's only one node, then we want to do this stuff here. We want to copy the data that's in that node into our temporary variable. If there's only one node, the head and the tail both point to that node. Okay, so it looks like this. So you copy the D over there. Then you need to call this delete function in C++, which deallocates the memory that you know, when you created this node way back in append, you used new to create this node. You need to delete it. That's why we had to store this D in here, because we're deleting this, you know, and otherwise we would lose the data that's in there. Then initialize the head and the tail to point to nothing, so that you have an initialized empty list here, and then return the data. Okay, if you have more than one node, then the difference is you're going to have to scoot the head down. Okay, because you're removing at the head. So initially the head points to a node, and then the tail points to another node. And here I've drawn 3 nodes in between there. There could be basically 2 or more. The reason you'd be down in here is because there was 2 or more. Because if there were 1, you would have bailed out over here in this return. Anyway, initially set P to be the head, so that P and H both point to this first node. Then scoot the head down, okay, to point to the next node. This is head equals head next. That is the value that's in this field right here that points to the next node. Write that to H, so that H points to the next node. Then take this D and stick it in temp, because we're going to delete the data that P points to. When you do deletes, you're not deleting the head pointer, or in this case the P pointer itself. You're deleting the data that the pointer points to, right? If you haven't used delete and new before. So P is still a local variable here. It's still around. The variable P is still around, but what it points to, that is the node down here, is deleted. All right, and then return this guy. So what's the time complexity of this? Do you see a loop with n? No, you don't. It's just constant time operations. So the time complexity of this thing is big O of 1. All right? That is, it takes the same amount of time regardless of how big the list is for this particular operation. Okay, we got one more operation to look at, and that's the most complicated one. We've got the find operation. This one's ugly or big. So what does find do? Find searches the list for an element, and if it finds it, it removes that element and returns 1. Otherwise, it returns 0. So we pass in an element that we're looking for, or a value we're looking for, D. And I've got a couple of pointers here. So let's go through each of the cases here in detail here. So if the list is empty, that's actually not, it doesn't have a picture. If the list is empty, so I didn't even draw that. The list is empty, basically the head and the tail point to nothing. Looks like that. There's nothing to do, so just return 0 and leave. Okay, if the list contains only one node, then your situation is you either that node either contains the data you're looking for or it doesn't. So you know that it's only one node because the head and the tail pointer both point to the same node. So you check, is the data in that node the data I seek? And if it is, I need to delete that node, set the list to be empty, print not found, returned that a 1 indicating that I didn't find it. Okay, if the data that's in here is not the data I seek, that's the else clause. I just, oops, there's a typo in here. This should be found, and return 1, and then not found, return 0. Sorry about that. Okay, so that's the case for empty and the case for one node. Okay, the case for, so I ended up breaking this up into 2 cases because the details of what you have to do are slightly different. So I broke it up into 2 cases. The first case is 2 or more nodes. So if there's 2 or more nodes, then, oh, wait a minute. No, it's 1 case. Yeah, this is all 2 or more nodes, but there is some stuff to do down in here. So basically what happens is the data that you find could be at the head, in which case I got to scoot the head pointer down, or it could be somewhere after the head, in which case I have to do something different. That's basically what happens. So I set up 2, way back in here I declared what I'm calling a cursor and a precursor. They're just 2 pointers. And you set this guy up so that the cursor is pointing at the guy after the head, and the precursor is pointing at the head. So PC equals head, that precursor is pointing at the head, and then the cursor is pointing at the next guy after the head, which happens to be, well, in this case, it could be the tail. But if the data that you're seeking is at the head, you have to do this stuff right here. You have to scoot the head pointer down so that it points to the next item. Then you have to delete this node up in here, all right, and return -1. So that's what's happening here. You head equals head next. You're pointing, that is, you're updating this head pointer so that it points to the next item. Then you're deleting the node, this node over here, using the PC pointer, and then you return. So that's what you do if the data was found at the head. You have to scoot the head pointer down, basically. If the data was found after the head, well, then you got to do a couple of things. First, you got to find it. So we have to look for it. Let's see. So we have to look for the data. So basically we have to walk the PC pointer and the C pointer all the way down to the end of the list. So the loop will terminate when C falls off the end of the list, or when C becomes 0. So that's this while C that terminates the loop. So C will contain some valid address until it reads in the null that's here, and then it'll point to nothing. So yeah, that's what this while C is. C is walking off, and then you're incrementing PC to be C and C to be C next. You're basically moving the PC and the C pointers down, and then when you find what you're looking for, this if stuff will be true, right? When C's data is equal to the data you seek, right? In other words, when the C pointer finds the node you're interested in, then you got to do a couple of things. Basically, you got to cut out the node that contains the data that you found, right? So once again, PC will walk all the way down and C will walk all the way down. C will stop when it finds the data here. And at that point, you got to do some snippy stuff and then leave. What you have to do is you have to make this guy, this node here, point to the node after C, then delete C, or delete the node that C points to. So okay, so this pointer here has to be updated to point to this guy. So that's this line here. PC next, which is this field, needs to be the value in C next. So whatever this guy pointing to this guy, you have to put that value over here. So now this guy points to that guy. Okay, you have to do that. Then delete C. Then there's a little bit of an implementation detail. It's possible that you could find the data at the tail. Right, that's possible when this loop is executing. In which case you got to scoot the tail back 1. Okay, so if for the special case of the data being found at the tail, if C equals tail, that's how you know that you found it, because you're inside here where you found it, and C is tail. Then you need to scoot the tail back 1 there. Okay, so this is it, and this is as complicated as these kind of pointer things get. Before we leave this, what's the time complexity of this operation? What is the big O of this find operation? There is a loop. Well, first of all, there's all this constant time, John. This is just, there's no loop, up here. But then here, here you get to a loop. And what's the worst case for this while loop right here? Worst case is C and PC you're going to run through every item. So the worst case time complexity is n. So the find operation has a time complexity of big O of n, because worst case, you look at every item. That's the same, by the way, as the time complexity for the circular array, which I happen to have over here. This is the find operation for the circular array. It runs through every item, so it has a time complexity of n. The linked implementation runs through every item. It also has a time complexity of n. So these two implementations both implement the same interface. That is the same set of functions: remove, append, find, traverse, and is empty. And for this particular data organization, these all happen to have the same time complexities. So there doesn't seem to be any difference between the Toyota and the Ferrari here. Either one they seem to operate exactly the same. They go at the same speed when you step on the gas, so to speak, or they carry the same amount of people. So that's just for this simple little list implementation. That happens to be the case, but it won't be the case for other kinds of data organizations that we're going to see in a bit. All right? So that's just the basic idea of a simple container that implements a particular interface, and we've implemented that container using two different implementations: a circular array and a linked list. Okay, I'm going to wrap it up here. I'll refer back to this material in the next video a little bit. All right, I hope this was useful to you. Hope it was at least mildly entertaining. And I'll see you next time. Bye-bye.